Alright, so here we're going to be looking at an example on how to perform stoichiometry. So here is our problem. Let's say we have here 1.000 grams of butane, and butane is C4H10. And this is going to be a combustion reaction, so how many grams of oxygen are we going to need? And how many grams of CO2 and water produced? Alright, so here's our problem. We're taking 1 gram of butane, we're burning it with oxygen, and we're producing carbon dioxide and water, and we just want to figure out, well, how many grams of oxygen are needed, how many grams of CO2 and water are going to be produced here. So the first thing we're going to need, of course, is a balanced chemical reaction, because you need that before you start anything with stoichiometry. So this one is a little bit complicated, so we'll just give the balanced one to start off with here. So we have here 2 butanes plus 13 oxygens, and this is going to give us 8 carbon dioxides plus 10 waters. Now the reason I chose this particular example here is, as you'll notice, all the stoichiometric coefficients are different, so 2, 13, 8, and 10. I did that because sometimes if you have 1s or all 2s or something, and then you just might say, well, I can just simplify, I don't need this middle step. But here, by having different coefficients, it explicitly shows you why you do need to do all the steps. You can't just, do a little simplifying and skip over something because it happens to be 1 over 1. So this reinforces that. So the first thing we want to do is go through here and see what information is given in the problem. What we have here, 1 gram of butane. So this is our known thing, 1.000 grams of this stuff. And then what we want to figure out is, well, how many grams of that, how many grams of the CO2, and how many grams of the water. Then the next thing that we need to do is figure out, well, what are my molecular weights for each of these? So here, carbon is 12, hydrogen is 1, so that's 12 times 4 is 48, plus another 10, so that's going to be 58. So this is 58 grams per mole. Oxygen, that's 16 times 2, so that's going to be 32 grams per mole. Carbon dioxide, well, there's 32 from this, plus another 12, that's 44 grams per mole. And water, that's 16 plus 2, that's going to be 18 grams per mole. From this point, we really have all the information we need to start writing out our equations. So the first one we'll start off with is, we'll just do these in order, the oxygen, then the carbon dioxide, and then the water. So the first thing we want to do is write out how much butane we have here. So that's 1.000 grams. And here, don't just write grams. You also want to write what grams of what you actually have here. So that's going to be grams of my C4H10. And then we're going to need our molecular weight, because we need to take this number of grams and convert this into moles. So this is going to be 1 mole of the C4H10 is 58 grams of the C4H10. Then the next thing we need is our mole ratio, and that comes from the stoichiometric coefficients. So since we're dealing here with the oxygen, we're going to want the oxygen here on the top, because also if you look here, we have moles of our butane. We need that to cancel out. So that what this is saying is that there are 13 moles of oxygen for every 2 moles of butane. So that's going to be 13 moles of oxygen. It's 2 moles of butane. All right, and then from this point, we have how many moles of oxygen. So here we can just figure out how many grams of the oxygen we need. So this is going to be 32 grams of oxygen is 1 mole of oxygen. And to show why it is so important that we actually do write out all of our units here, notice right here I have grams of butane, grams of butane. So, these cancel out. I have moles of butane, these cancel out. Moles of oxygen, these cancel out. And I'm left here with grams of oxygen. So if we go through and calculate this, we get 3.586 grams of oxygen. So that's the first one. Next we move on to the carbon dioxide, and really it is exactly the same process. Okay, so really, these first 2 things here are going to be exactly the same. Now over here, our mole ratio, well, since we're not using oxygen, we're using carbon dioxide. Now we're going to be using the CO2 over here. That's going to be 8 moles of CO2. And still, we're still dealing with the butane, so that's still going to be the 2 on the bottom. And then just like before, we multiplied this by our molecular weight, so that's going to be the 44 for the CO2. And just like before, grams of butane cancel out with grams of butane, moles of butane, moles of butane, moles of CO2, moles of CO2. So we're just going to be left here with how many grams of CO2, and that works out to be 3.034 grams of CO2. All right, and then we just have the final one here, which is for the water. So again, first part is exactly the same. And then over here, now we have 10 moles of water to 2 moles of the butane. And then we just have to multiply this by the molecular weight. And that works out to be 1.552 grams of water. This is why, it is so important to go through here and explicitly write out what I'm talking about, moles of what. Otherwise, if you just write there grams and moles, especially right here, this is where a lot of people goof things up, because you're going to say, well, is it 8 or 2 or 2 over 8? But, because if it's just moles over moles, moles cancel out, it doesn't really matter. But here, if you explicitly say moles of CO2, moles of butane, you know which goes on the top and which goes on the bottom, because otherwise, this will be very easy to screw this up without knowing what it is. So just make sure you explicitly say moles of water, CO2, oxygen, butane. This makes that 100 times easier. If you don't, you have like a 50-50 chance of goofing it up. One way that we can check just to make sure that we did all of our calculations right is mass conservation, right? The amount of butane and oxygen I put in, so the mass of these two things, should be equal to the mass of these two things if you did all your calculations right. We look here, 1.000 grams plus my oxygen, 3.586. That's going to be equal to, obviously, 4.586. And if we did our calculation right, that should be equal to this. So the 3.034 grams of CO2 plus the 1.552 grams of the H2O. Obviously, let's see, 2 plus 4, that's 6. 5 plus 3, that's 8. 5 plus 0 is 5. 1 plus 3 is 4. So yes, this works out. The amount of butane and oxygen is equal to the amount of CO2 and water, all right, which it should be because mass is conserved. If it didn't, you goofed up. And then that's where you go back and double check your calculations, make sure you entered everything right in the calculator. If you are doing these things, sometimes due to rounding errors, the last decimal place might be a little bit off. So we might get here 4.586 for this side, and this side might be 4.587 or 4.585. If that happens, it's a rounding error. Odds are you did everything correctly. It just happens to be a rounding error in the last decimal place. That's fine. But if you happen to get here, 4.586 and this one's 10, you goofed up somewhere and you definitely have to check things out. So make sure you did your calculations right. Also, make sure that all your molecular weights are right. Sometimes it's easy to goof up on these if you're not careful. Also, just double check to make sure your stoichiometry is right. Just go here and say, okay, how many carbons do I have? 2 times 4, that's 8. That works out. 2 times 10, that's 20. 10 times 2, that's 20. And then oxygen's 13 times 2, that's 26. And here I got 8 times 2, that's 16, plus another 10, that's 26. So, you just go through and, just double check everything just to make sure everything is good there. And this is just a final little thing to check that. Now, you might be saying, well, I did this one and I did this one. Could I have just used subtraction to figure out how much water I have? If we have this, and since this is going to be equal because of mass conservation, you could theoretically figure out the mass of your water just by subtraction. I advise you don't do that, because what's very easy to happen here is you accidentally mess up someplace over here, and then there's no way you can actually double check your work. Okay, so if you just do that, you basically skipped a step, and then you don't know if you actually did something right or wrong, because you're going to get a weird result there. So just do it this way, and also, the main thing here is look at the pattern we're actually using. All right, here we're starting off with the grams of our substance that we're starting with, converting this into moles, using the mole ratio, and then converting it back to grams. Okay, this is the basic thing. And even if you mess things up here, it's always write out your units. If you write out your units, it takes you an extra 30 seconds, but it saves you a lot of hassle and second guessing yourself with these. So here, the basic thing that we did for all these calculations right down here, we had our number of grams, and then we converted this into moles, and then we used the mole ratio. Actually, that would be moles per gram, and then we have here our mole ratio, and then here we have here grams per mole. Okay, so again, just look at where the grams are right over here. This is on the top, this one's on the bottom, our moles are there. So it's one of those things, just practice. And here, go through this calculation, just starting off with the information we had up here, and then do these explicitly yourself. If you can do this very easily, you'll have no problem. If you keep goofing up, keep trying it until you get the pattern down.